let's see, what example did we do? We did one example at the end of the lecture where we talked about the coefficient of expansion. Which one was the one that we did? Oh yeah, the ball fitting into the cylinder, right? And then we did, okay, how much does it have to be heated up so that it barely fits in? So let's try something else. Let's see, based on these numbers. So let's say we have a spherical ball. So let's say you put one of these liquids in there. Let's say petroleum. You have imagine you got the spherical ball here, and it's a hollow sphere, and then you put it as a container, and you put the petrol in there, and they're both going to expand. And then as it expands, if the petroleum expands more than the sphere, part of it will spill over. So let's assume that there's a little bit of a hole, right? A little bit of a hole, so that if the petroleum expands more, part of it will spill. Okay, but if the sphere expands more, then actually the sphere will be able to contain. So we can say how much of the petrol spills over, or how much volume of empty space is left in the bowl. So if the bowl expands more, then there's going to be some empty space left over, right? So let's give the materials of these things. Well, petroleum, we already have here the beta of petroleum, 950 times 10 to the minus 6. Beta of petrol, 950 times 10 to the minus 6. And then let's say the bowl is made of brass bowl, let's say. So alpha of the brass is going to be what? 19 times 10 to the minus 6. Right? Okay, so now, how should we do it? The equations that we have from Monday are, if it's a linear expansion, it's delta L is alpha, L initial, delta T. If it's an area expansion, the dA is 2 alpha, A initial, delta T. If it's a volume expansion, 3 alpha, A V initial, delta T. So these are the ones we use for solids. And then for liquids and gases, we use, but we're gonna pretty much concentrate on liquids. For we use dV is beta V initial delta T, right? So this solid expands, right? What should we do? Should we treat it as volume expansion or area expansion? The thing is, the solid is two-dimensional surface, but it also has a volume inside, right? But if it's a hollow solid, should we treat it as an area expansion? Because it's not really a solid sphere, it's a hollow sphere, right? I think this one we should do area expansion, not volume. It's not like the sphere the other day where I was saying you warm up a sphere and you put it into the cylinder, so how much it should be. Okay, now that one, there was a whole solid sphere, its volume expands, and then we use this equation to find out its new radius, right? For this one, yes, there is inside empty space, but the object is only two-dimensional. Its thickness of the cylinder, the thickness of the sphere is minimal, right? So we should use the area.
I mean, it's not a solid.
It's not a solid sphere. Yeah. So it's kind of, at first it fakes you. You may think you should use the volume. See? So I think we should use the area. So then we're going to do dA is 2 alpha A initial delta T. And the alpha is going to be 19 times 10 to the minus 6. The area initial is going to be what? The surface area of a sphere, right? 4 pi r squared, right? 4 pi r squared is the initial surface area. So what was the initial, the radius? 2, right? 2 meters. So 4 pi r squared, that's the initial surface area. The change in temperature is, it went from 25 Celsius to 80 Celsius. So 55 Celsius. So this gives you the change in area, okay? How much the area increased by. Okay? That's meters squared. Okay? So now, from there we can find out the final area, right? What's A final then? A initial plus delta A, right? So then you take the original surface area, 4 pi times the radius squared, you add this number to it. So the area doesn't change that much, of course, but it slightly increases. So you add 4 times pi times 4. So now the new area becomes 50.3705373157. Okay, now from there what can I do? My eventual goal is what? To do what? Well, I want to know how much of it spills over, how much of the liquid spills over, and how much of the solid, or if the solid expands more, I want to know how much air is left inside, right? So my ultimate goal is to find the final volume of the brass ball, the final volume, and then from there I can calculate which one has the bigger volume, right? So my goal is to find the radius, right? Say this one is the final area, so then we can have 4 pi r final squared, right? So then from there I can calculate the final radius, right? So divide this by and then square root it. So you have our final squared is going to be 4.00836, then square root that. I'm not rounding too much so that, because since the numbers are small, I'd rather keep as many sig figs as possible. 2.0020889. Okay, now from there, what can I do? I can calculate the new volume inside of that sphere, right? So I calculated the final area. From there, I calculated the final radius. Then from there, I calculate the final volume. Which is 4/3 pi times this radius cubed, right? So that will cube that number. Meters cubed. So that's the final volume of the bowl, right? Now I'm going to go to the liquid. What was the initial volume of the liquid? Well, initial volume of the liquid was the same as the volume of the original bowl, right? And then the change in volume of the liquid, we're going to use beta V initial delta T, right? So delta V is going to be beta V initial delta T, for this is for the liquid. Beta is going to be what? 950 times 10 to the minus 6. V initial is going to be 4/3 pi 2 cubed, because that was the original volume, the original radius of the bowl. So that was the original volume of the liquid, right? It was completely full originally. 950 times 4/3 pi r cubed times delta T, which is 55. So then delta V is going to be okay. So then what? Then from there, I add that to the original volume of the liquid, which is the same as the volume of the bowl. So V final is going to be V initial plus delta V. So then it's going to be 4/3 pi r cubed plus 1.7509143.056. Oh, wow. Oh, yeah, the liquid is more, 35. This is 33. So my hunch was that the liquid was going to expand more, because especially the liquid is 950. Liquids expand more than solids usually, right? So how much of it is going to spill over? This is meter cubed and meter cubed, so then you just subtract them, right? V spill, subtract those numbers. Okay, so 1.645 spills over. So it's a good practice in using these equations. First determining which one you should use. Should you use the area or the volume, right? And then in this case we said since the ball is hollow, we should use the area. Then from there, calculating the radius, calculating the volume. For the liquid, it's a little bit more straightforward because liquids only expand volumetrically, right? So that for liquids, you just use that one. And then you combine them and pair them. Pretty good problem. Okay. Maybe let's do one more. So those of you who just came in, get this problem from someone or watch the video later. It's a good problem that might be on Monday's test. So now another one, maybe let's do this one. Let's say there's a big slab of concrete, right? And they didn't design it well so that it's kind of long and they didn't put any joints for it to expand. So let's say it gets really hot on a day, 25 Celsius, and the concrete becomes, well, let's make it the same temperature that we just had. So let's say on a normal day it starts 25 and the concrete gets to 80 Celsius, right? Because the concrete does warm up quite a bit easily. So then we have the alpha of concrete right here. So 12 times 10 to the minus 6. So now let's assume that it develops a crack on one side of it. It starts cracking. And then these two sides, this side expands this way, this side expands this way. So there's probably something else going on the other side. Maybe there's another concrete. So it's like complicated chain of events. But let's focus on just this one slab. So if the distance from here to here is, let's say, 4 meters, let's say this is 1 meter. Okay, so this guy's going to expand this way, this guy's going to expand this way. So they're going to lift each other up, right? So can we find this distance? H. It's a little bit of a geometry problem again, right? So they push on each other and they get lifted a certain distance. So if this original length was 4, the amount that this expands is more than the amount that this expands, right? Depending on where the crack develops. So this guy expands less. So how do we do that one? Here we know that the length of this is going to be what? L final is going to be L initial plus delta L, right? And then delta L is alpha L initial delta T, right? So the final length here is going to be L initial 1 plus alpha delta T. Okay, and then let's call this guy, let's say this is L final. Let's call this guy maybe little L final. Little L final is going to be similar equation. Little L initial 1 plus alpha delta T. So the only difference is that that one was 4 meters to start with, right? 4. And then this one was 1 meter. These two angles are probably not the same, huh? Alpha and theta. What can we say? Oh, okay. So maybe we can say this distance here has to be what? 5 meters, right? From here to here. It has to be 5. So what if we say L final cosine of alpha plus L final cosine theta must equal 5, right? Oh, okay. So now, what's cosine of alpha? It's going to be this distance from here to here over that, right? Well, what is this distance? This distance is square root of what? L final squared minus h squared. Aha. Let's see. Because this is a 90-degree angle. So this is L final squared minus h squared. So cosine alpha is this over that, right? So L final cosine alpha plus L final cosine theta must be equal to 5, right? And then cosine alpha is going to be square root of L final squared minus h squared over L final plus L final cosine theta, which is going to be this guy, L final squared minus h squared over L final. This cancels this. Okay, so then you have here square root of L final squared, which is this guy, right? That guy squared. 4 squared 1 plus alpha delta t squared. Oh, you know what? I should call this something other than alpha. It's the symbols that confuse. This is phi. But I really didn't need the angles. I just put them there just to visualize what's going on. So then I'm going to have this guy is going to be L final squared, so minus h squared plus square root of this guy squared, 1 plus alpha delta t squared minus h squared, and that's equal to 5. Right? But now I actually know what my alpha is, and I know what my delta t is, right? The alpha is 12 times 10 to the minus 6, and delta t is 55, right? So I can put on those numbers, I can put those numbers in here, and then the rest I can just put it in solver and solve for h. Right? So my delta t, let's see here, 1 plus rho times 10 to the
What would change in T or delta T be?
But it started at 25 and 80.
80, there we go.
Yeah, same
Okay.
as the previous problem, so I just kept it the same.
Got it.
So then you have here, this is going to be 16.000384 minus h squared plus, and this is going to be, well, it's going to be similar to this, except it's missing the 16. Right, so I can just divide this by 16. So it's going to be square root of 1.000004024 minus h squared is equal to 5. Okay, then put that in solver. Okay, So it shows that this chapter there's quite a bit of geometry that you can do, you know, where the problems is really visualizing what's happening, how much things are expanding by. Um, 384 minus x squared. Square root minus 1.0000024 minus x squared. Square root is equal to 5. It says false, no solution. No solution.
Square everything. Can't square this.
Oh, hold on. I put a minus here in my equation. I think this was minus. I just thought that everything is minus. Oh yeah, there you go. 9.797 millimeter time, because it says 10 to the minus 3. So 9.79789 millimeter. Is that considerable? So when walking over that concrete, would you notice that? 9 millimeters is about almost 1 centimeter. Yeah, about this way. Yeah, it is noticeable. Right? So you go like this. You gotta fix your. You say you've got to fix your driveway, right? Because if you don't if you don't fix that over time, it's going to develop more cracks, and then it's going to get higher. Then a kid comes and falls over it, and you get sued, right? Right. So your knowledge of expansion coefficients, you say, okay, yeah, I should fix that. It's a good problem. Okay, as always, we can keep doing more and more, but for brevity of time, we now go to the next chapter, chapter 20.